In your house and you are listening to your smart radio. You just hear the latest Taylor Swift song come on and you're really excited. You run over to your radio and you press the button, and that button saves that song to your profile online so that at a later date you can come to it on your computer or your phone, look at it and maybe download it and learn the lyrics. But how on earth does this smart radio know what that profile is? You certainly haven't used those few buttons to enter in a username and a password. That would be an absolute nightmare. So the way that you get around that is often to pair your smart device with a dumb input with something that is far better suited for entering text, like your mobile phone or a laptop. The way that this works is that your smart device will generate a code at random itself, present it, and it's time sensitive, which means that when you then type that code into your phone or laptop whilst logged onto your service, that radio will then know, aha, that's the profile that I'm associated with. And it gets around the problem of needing to work out how to enter an @ symbol on your radio. So it sounds like we've solved the problem. Pairing works. But we have an extra question now. What should these access codes look like? It is possible to design a really crappy code. Think about the last time you went to your friend's house and you tried to log on to their Wi-Fi and they hadn't changed the password for it. You saw something like this and you were very frustrated, you messed up a few times, and it was a generally bad experience. It shows us that there is an opportunity here to think about designing codes. Why is this particularly interesting? Well, if we kind of pull back and think about data entry tasks in general, we can see this provides us with a really interesting task. So I do a lot of work with people entering data on medical devices, where they might be entering a prescription into a device that will administer drugs to a patient. One way we can reduce errors and make it a better experience might be to redesign the interface. So, for example, I've shown that you can significantly speed up an interaction if you look at the frequency of numbers being used and just add some extra buttons to the device. Another way that we might improve the general data entry task is to just redesign the task itself. One other piece of research I've conducted showed that if you ask people to enter additional numbers in the process, you can significantly reduce the number of errors that they make. Another piece of research that we've worked on shows that if you lock people out of a system after they've been interrupted, that will also reduce the number of errors that they make. You can find out more about that on Wednesday at 9:30 in the multitasking experience. So yes, go to that on Wednesday. But here we have an even more interesting question. With this pairing situation, we can think about redesigning the data itself. So we no longer need to come across horrible codes like this. So, if we're going to design an access code, what does it need to do? Well, firstly, the access code needs to be secure. Whatever algorithm it is that generates the access code needs to be able to produce a large number of possible codes to prevent something like a brute force attack. In the situation we're working with in this experiment, we needed at least 500 million possible codes. The second thing it needs to do is to be alphanumeric. So these codes are going to be displayed on devices that might not necessarily have a high-fidelity display. You couldn't, for example, present a QR code on an LCD screen very easily. So the codes that are produced need to be able to display on a wide range of devices. So they need to be alphanumeric. So what codes did we test? Firstly, we looked at alphanumeric because that seems to be a very popular one. An alphanumeric code is one made up of lowercase, uppercase, and numbers, number characters. For example, 4Y3PG. In this situation, we've removed any characters that look quite similar to one another, like the lowercase L and the number 1. And that leaves you with a range of 56 possible characters. With such a large range of characters, it's possible to create a very small code. So with only 5 characters from that set, you can create a code space of over 500 million. The second possible code that we looked at was a numeric code. This one is just made up of numbers, and there are 10 possible numbers. I don't know if you know that. And so in order to create a code that was a code space larger than 500 million, you only need to stick together 9 of the characters in the numeric codes. Now, the third one is a slightly stranger option, it might seem initially. In this condition, the words condition, it was comprised of 3 three-letter English words, you, any, cat. Now, at a conservative estimate, there are 800 possible 3-letter words that are familiar to an English speaker. And with that large number, you need to combine three-letter words together, creating a space of over 500 million with only 9 characters. Now, it might seem counterintuitive at this point. The alphanumeric code is a lot shorter, and so therefore you might expect it to take a lot less time to enter. And so maybe that would be the best option. So why are we even looking at these other 2 options? Well, there's 2 reasons for that. Firstly, we know that entering mixed characters on phones is a very difficult task. When you compare these 2 codes below there, the one on the left requires you to switch between all these different keyboards, adding extra steps and extra workload to the process, compared to the one that's all single characters. So the numeric and words codes, for example, would not suffer from this keyboard switching issue. Secondly, we know that copying random strings is a lot slower than copying words that we're familiar with. So if we were to copy the word ipsep, we would do it a lot slower than we have to copy the word puppies, even though they involve the same letters. It's because we know the word and we have it stored in our memory, and so that facilitates the typing process, meaning that the words codes might not be so stupid after all. To test this, we got people into a lab. In the lab, there was a display screen showing the codes one at a time, and the participants then had to copy each of these codes. Again, we've wanted to do this on mobile phones and laptops because there might be some difference, and we think these are the 2 devices that people are most likely to use. So of the 20 participants came in, they typed 3 different code types on both of the devices, and they did 20 trials per code type, meaning that each participant had entered 120 codes in total. So what did we find? Well, one of the key things we need to think about here is speed. So from the time that the code was displayed on the separate screen to the time they pressed enter on their device, we timed it, and for average speed for word codes was significantly faster than those for alphanumeric and numeric, suggesting that it's not just the length of characters that you have to type, there's also something else happening. I should note that the error rates for all 3 of these conditions was the same, meaning that we weren't trading accuracy for speed here. So what could have been causing words to be so much faster than the other 2 codes? Well, we tracked eye gaze data during the experiments, and if we look at the number of fixations that participants made during these trials, we can see that in the words condition, they made significantly fewer fixations than the other 2. This suggests that the words codes were more easy to remember, and that meant that the participants didn't need to look back and forth between the screen and the device they were entering on. So these 2 metrics suggest that the words condition was better and had better performance, but were the users aware of this themselves? We asked the users after each condition to fill out a NASA TLX survey to assess the workload. And when summed and averaged over each participant, we find out that words were deemed to be easiest to enter by the participants. So not only were the performance metrics suggesting this was the case, but the participants themselves were aware of it too. So, in conclusion, the word-based codes, despite being longer than alphanumeric, were just as secure, were faster to type, were no more error-prone, and were considered less taxing to copy by the participants. So I suggest to you that if you're ever in the unique situation of being able to design the data for a data entry task, you might like to consider words rather than the standard alphanumeric or numeric. So next time you're over at your friend's house and they have a terrible Wi-Fi password, you might like to point them in the direction of this paper, or maybe in the direction of this XKCD comic, which essentially has already done this work. Thank you very much.
That's a good question. So did they use their own mobile phones for this, or did you provide mobile phones?
Yeah, they used their own mobile phones for it, yes.
Was there a difference between like model or make and versus iOS? So we did some studies where we found actually differences between different smartphone keyboards and entering passwords on there. So that's
Yeah.
I'm interested.
I see, yes. We didn't specifically look at that. Is the thing that you're getting at how easy it is maybe to get to the numbers on an Android
Well,
phone
I'm just
compared to an
curious
iPhone or something like that?
but
Yes.
Okay.
We didn't specifically look at that, but I know there is some research coming out of UCL at some point that will identify that as a key issue, yes.
Hi, for the word condition, did you have people peck the words, or did some people use a swiping keyboard? Some keyboards have like built-in, like cat.
Yes.
Just versus I don't know if you at least took data about how people were entering on their keyboards for the word condition.
Yeah, no, we didn't measure that. We were just trying to ensure that it was as natural inputs processes that would occur in the world if they were really using it. So we allowed them to use whatever input method they wanted, and no, we didn't take a note of that. But that's an interesting point. Yeah.
Hi.
Hi.
Nice work. Quick question. So, why is it that the code itself has to be so long and cover such a large space? Because potentially you would argue that the number of people who are in the room who can potentially see the screen or guess it is relatively small, and if the time window is relatively short, why can't I just give you a 3-digit code that is trivially simple and be sufficient?
No, that's a good question. So we were designing the system to be a bit more generalizable than the one I just gave you there. So there may well be a situation in which you have a smart television, for example, and you're asked to, and you might want to save a TV program to your profile somehow. Now, in that situation, it is very possible that a TV program may suddenly go, hey, if you're watching now, why not pair your TVs? Why not do this? And so there may certainly be a case where there is an individual instance that encourages a very large number of people to all pair at the same time, necessitating a very large code set.
Hi, thanks for the talk. I'm Marian Harbeck from Audi. I was wondering if you were also thinking about using just 4-letter words and then 2 of them, because if you get suggestions from your keyboard, as Janice was getting at, or something like that, it might even be quicker with that.
Yeah, that's a very good point too. Yes, I think the way to think about it though is that there are definitely going to be instances where people are using their laptops as well, but
right.
2 4-letter words. I guess
And
it
then
depends
there
on
are
what the
also more than
search space
800
is.
probably, right?
Yes, exactly.
Yeah.
Good point. Yeah, no, we didn't consider that. This was something of a proof of concept to compare the words to alphanumeric to numeric, but there's definitely some optimization that can be done there. Yeah, thank you. Cool. Oh. Thank you.